already here as well? Yes, Miguel is going to be the chair of this session as well. Great.
Okay, so just confirming, you can see my slides and they're moving, right?
Yeah, we can see your slide. Miguel, it's all, Miguel? Yes, it's all yours.
Yes, can you hear me, right?
Mm-hmm.
Okay, great. Thank you, Professor George Konidaris. Professor George Konidaris is director of the Intelligent Road Lab at Brown University. He works in the area of machine learning, reinforcement learning, and optimal control to build intelligent, autonomous, and general-purpose robots that are generally capable in a wide variety of tasks and environments. So please welcome to Professor George Konidaris.
Thanks, everyone, and thank you all for the invitation. It's a great pleasure to be able to speak to you. I'm bummed that that we can't do ICDL in person this year, but hopefully in some subsequent year, I'll get to meet you all in person. That would be great. Okay, so what I'm going to talk about today, I'm going to talk about sort of two topics that are being plugged together recently in my lab. So the first one is learning grounded symbolic representations for robots, and the second one is how we can sort of begin to use those grounded symbolic representations for communication. So in my lab, and I think this is true of many of you, we're interested in like actually doing AI, right, rather than just solving useful problems or something like that. And so it's useful to highlight what's different about kind of real AI research versus just making useful stuff. And the key thing for us, I think, or the key thing that we focus on is that intelligence is not the ability to do a single thing extremely well. It's not the ability to be like the world's best backgammon player or something like that. It's the ability to do almost anything reasonably well. Okay, and so that's why we're roboticists in my lab, right? Because we think that in order to be able to do almost anything a human can do, that you need to be a robot. You can't be just a computer. And so we have this model of this process where, which is fundamentally a sequential decision-making model. So we have a robot and we have the world, and the robot can take actions in the world, and it gets observations about the world. Okay, and that's just a description of what happens when you get a robot and you plug it in, right? It has sensors, they come, they register sensations at some frequency, and it has joints, and you can kind of actuate the joints using torques. And then we're going to model a task, because we said, the robot needs to be able to do many tasks. We're going to model a task as a reward function or a utility function that we're going to be able to give to the robot, and it should be able to kind of learn to take actions to maximize that task. So this is a reinforcement learning style setting, and we're going to say that the task is drawn from some distribution over tasks. Okay, so it's gonna see these things over time. And where we differ from the more traditional reinforcement learning setting is that we really want to model robots that are sensing and acting in the world, not the task. Okay, so it's not the case that this is a robot built to solve one task. It is the robot that perceives the world using very rich sensors and actuators, gets to take actions using very rich motors, and it's going to use the same state and action space for all the tasks that it's going to solve, because it's the same robot. But it's really interacting with the world, not the task. And so to sort of to really hammer home what that means, if you care about just solving one task, and you'll see this all over AI, right? It's the assumption that they're making that's so basic they don't even know that they're making it. When you are applying learning or AI to a single task, you just get given a nice state and action space that describes that task, right? If you want to learn to play Go, we say, well, the state space is all Go boards. That's like a 19 by 19 array, and there's one of two types of pieces, or it's empty, or there's a piece, and the pieces are one of two colors. Or if you're learning to recognize pneumonia in an X-ray, then the input is like a sort of aligned X-ray of someone's chest, and the output is like a label that says, there's illness or there's no illness. Or if you're learning to, play Jeopardy, then the input is a sentence and the output is a question, and here's an objective function that represents that. And in most of AI, they just assume that that's given to you, like that's just part of the formulation. It just magically appears. And of course, if we're trying to build a generally intelligent robot, that's not the case. You have to solve all these problems in the same sensory motor space, right? That's the kind of core question for me of how we are able to get to general AI. That's the kind of missing step. If we're given problems in these nice, well-formulated representations with a nice objective function, and they live inside a formalism like reinforcement learning or multi-arm bandits or classical search, then we sort of know what to do. But the agent actually has to build that thing itself, right? It doesn't get that for free. Instead, it has to interact with the world and solve all these problems using pixels and motors. Okay, so we call this the sensory motor dilemma. The more general your agent is, the larger set of tasks it has to be able to solve, the more complex its sensors and actuators have to be, and therefore the worse, and therefore the more badly suited they are to any individual task. So we're trying to think about how you might be able to resolve this, right? How you might be able to get around the fact that you and I have to solve even the simplest tasks like tic-tac-toe in a very rich sensory motor space. And so the formulation that we've come up with is looks like this. It says that you start out with what we call the ego process, which looks like an MDP. Actually, it's a POMDP, but for this talk, we'll just pretend it's an MDP. Where there's state and action, and I've given you a reward function, and that looks like a giant MDP in a huge, rich state and action space. But I'd really much rather be solving this tiny little MDP that describes the problem. It's got nothing to do with the robot, right? If you want to play tic-tac-toe, it doesn't matter how many joints you have in your robot or how high resolution your cameras are. Really, you would like to be able to shrink down to just thinking about, a 3x3 board with one of two types of checks on it, right? There's like a natural innate complexity that is attached to tic-tac-toe, and then there's the wildly overblown, overpowered complexity that is attached to your robot. And we'd like to be able to get between these two things. And it turns out that this is something that we study in reinforcement learning under the guise of hierarchical reinforcement learning. And we now know that you can get from this one MDP to this other much more compact MDP by just doing two things that we study in reinforcement learning. One of them is state abstraction. In robotics, we often call this learning a symbolic representation, taking your perception and breaking it down to, or shrinking it down to a much simpler representation. And then taking the set of actions that you can do and taking it from joints and shrinking it down to something like, let's do the legal moves in tic-tac-toe. And if you can do those two things, the rest of the MDP formulation follows. Okay, so all you need to be able to do is you need to be able to learn high-level actions and then high-level symbolic representations that are both suited for your particular task that you're solving, and then you're in a nice, happy, problem-specific representation. Now, you have to do these two things in a way that are mutually compatible, right? So you can't do one and do the other and assume that they're going to work out. You have to think about how to sort of integrate them tightly. And I'm not going to talk about it in a lot of detail now, but if you think about this, you will see that almost all the existing paradigms in AI are special cases of something like an MDP. Right? If your MDPs, if the state and action space are discrete and you have the model and the transition function is deterministic, then you have a search problem. And if the transition function is adversarial, then you have an adversarial search problem. And if the state and action space are factored and the transition function is deterministic, then you have a classical planning problem. You can even get to classification. You can say, okay, if it's a one-step problem always, and you have that's what we call a contextual banded in reinforcement learning. And if you have demonstration data for that contextual banded, then what you have is supervised learning, right? So everything else can kind of just be viewed as a special case of this, right? This is sufficient to get to all the existing AI paradigms. And so what we're trying to build is a robot that starts with this rich sensory motor space and learns the right symbolic representation or the right abstract representation for the task at hand. And sometimes that's discrete and sometimes it's continuous. But the idea is that it's gonna learn itself into the way in which you or I would naturally solve this problem. So as I said earlier, this requires abstract states and abstract actions. I'm not going to talk about the abstract actions today, just to say that there's lots of people working on how a robot might discover abstract actions for a particular task. My own PhD thesis was on this. I really enjoyed this paper, not least because I think the room looked cool, but there are many other papers working on how you might discover high-level skills. I wanted to show off this more recent work, which I'm very excited about, which is about how once you have the high-level skills, you can learn the corresponding abstract symbolic representation from raw pixel data in a way that's kind of provably necessary and sufficient for planning. So I want to kind of show you this domain that we built. I'm not going to talk about how we do it because I don't have a lot of time and I want to get to communication. But we built this domain where there's a robot, it's running around. You can see there's a cupboard and a cooler. And I just built the motor skills. I said, okay, the robot can move between the cupboard and the cooler, and it has motor skills for opening and closing the cupboard and the cooler. And then there's a little switch next to the cupboard, if you can see it in the top right there. And I built motor skills for turning the switch. And additionally, there's an object. You can see the robot is holding it in the top right corner, which can be in the cooler or the cupboard, and the robot can pick that object up when it can see it. You note a couple things to notice. When the robot can pick the object up, it sort of holds it up here. So its sort of hand is high up. And when it's not holding anything, its hands are down. The other thing to notice is that if you can see in the bottom right there, where when the cupboard door is open, you can't access the switch, right? It blocks the robot's vision, so it can't see where the switch is. And one more thing, which is not obvious from these photos, is that when the switch is on, there's a light inside the cupboard that's so bright that you can't see stuff inside the cupboard, right? So the light's got to be off for you to be able to pick up the object inside the cupboard. Now you and I could write down a small MVP description of that domain. It would have variables in it like, is the light on or isn't it on? But we're interested in getting that thing from pixel data. So instead, what we do is we give the robot kind of sensed data that looks like this. More precisely, I give the robot its pose in the map. So that's an X, Y, theta. I give it a voxelization of the whole room. I've just cut out the cooler here, but I give it the whole room, and I give it its raw joint values. And then using the framework that we've built, I'm just going to ask it to execute these motor skills and observe which motor skills it can execute where, and what happens to those state variables after executing them. Okay, so it's just trying stuff out here. There you can see it picked up the object, it's turning the switch, it's opening and closing stuff. Let's see if there's a part where we can see, you can see with the light on, it's very bright inside the cupboard. And so we did about 160 executions of various motor skills, took an hour or two. And from that, we were able to learn an abstract symbolic representation that looks like the top left here. So you can see that that is text, right? That's a text file in a format called PDDL, which is a common one used for classical planning. And that says that if you want to navigate to the cooler, symbol 1 has to be true, and afterwards symbol 0 will be true, symbol 1 won't be true anymore, and it will take about 37 seconds to do that. But because this robot's learned this abstract symbolic representation, it's got groundings for all the relevant symbols. So these symbols, symbol 0 and symbol 1, are grounded in the robot's pose in the map. They're actually distributions over the robot's pose in the map. And so if you draw samples of those distributions and you visualize them, you'll see that like symbol 1 on the right there, the robot's kind of standing in front of where the cupboard is. And you'll see for symbol 0, it's standing in front of it and facing the cooler. So this says that if you're standing in front of the cupboard, you can execute navigate to the cooler, and afterwards you'll be standing in front of the cooler. And the robot has discovered this distinction, that this is the relevant one for making, for being able to plan, and it's learned that grounding, and it's built this text file, and you can throw away the grounding and you can just use the text file to plan. This is a more interesting grounded operator. This says that if you want to open the cupboard, symbol 1 has to be true, so you have to be standing in front of the cupboard. Also, symbol 3 has to be true. That's a distribution of the robot's joints. And so if we draw samples from the distribution, you'll see that the arms are always down. So the way to interpret that is that the robot's not holding anything, because when it's holding stuff, it's up here. And then you'll see symbol 4 is, it's a distribution over the voxels in the whole room, but I've just clipped out the cupboard, which is where all the variation is. And you'll see that there's a bunch of stuff. The switch could be on or off. There's a bunch of compression artifacts, but what's happening here is that the cupboard's closed. And then afterwards, it won't be the case that the cupboard's closed. Then it'll be the case that the cupboard's open. So it's learned this high-level symbolic representation that says if you want to open the cupboard, you should be standing in front of it, not holding anything, and it should be closed. Afterwards, it won't be closed. It'll be open, and it will take about a minute to execute that skill. Okay. And then once you have this, what you can do is you can take that text file, you can give it to a classical planner. It takes about 4 milliseconds to find a plan, and then you can run it. So this is an example. I've asked the robot here to move the object from the cooler to the cupboard. And so 4 milliseconds to find that plan, because of course it's not a very complicated state space. It opens the cooler first to see the object, but then it doesn't pick the object up, because if it did, it wouldn't be able to open the cupboard. So it moves to the cupboard, but then it doesn't open the cupboard because the light switch is on. And if it opened it, it wouldn't be able to switch it off. So first it switches off the light, then it opens the cupboard. Then it comes back to get the object. And the reason that this is slow is just because the vision processing is slow. I wrote all this code and I'm not good at vision processing, but the actual planning itself is extremely fast. Okay, so here it's coming back to go pick up the object, and then it'll take it and it'll move it into the cupboard. And also I asked it to clean everything up afterwards, close all the stuff. So at the end, it will, after it's dropped that object off in the cupboard, it will close the cupboard and it will close the cooler. And of course, this is what classical planning classically does, right? This is not surprising. Once you have that representation, what's interesting about this is that we learned that representation from scratch by just executing the high-level skills. And the upshot of that is that if we do have the high-level skills, now we understand how to get the corresponding matching high-level symbolic representation that allows you to do classical planning. Okay, so that's like what my lab has been working on. You know, this is our sort of main topic of what we're thinking about at the moment. But given this, I want to talk a little bit about okay, in this framework where we're thinking of an agent that's going to go around and learn all these representations, how does language and communication fit in? So we've done this in a bunch of domains now. We've done it in 12 different domains. I think 5 or 6 of them are real robots. But one of them, this RSS 2020 paper, was specifically about language and communication, right? If you're going to talk to a person, how are you going to be able to think about the grounding of, in terms of the symbolic representations, the grounding of the language that they're speaking to you? And so we have this kind of setting where we've got an agent and it's learning all these symbolic representations, and then you get a human, and the human comes along and gives it a command or gives it some information. And the first sort of takeaway that I want people to sort of carry away is, if you're thinking about language, communicating with a robot, the language has to ground to one of these decision processes. So there's 2 challenges here. One challenge is, people think about language grounding. They think like grounding to an image or grounding to a video. You've got to ground to a sequential decision process formalism, right? That's what you've got to ground to, because that's what robots solve. They're sequential decision process solving machines. And the second one is that there may be many different representations in the robot's head, and it's going to have to decide which one you're talking about. When you say kick the orange ball, that doesn't apply to chess, but it does apply to RoboCup in this case, right? So these are kind of different orbiting representations that the robot might have, and when you're talking about one of them, or maybe multiple of them in a sentence, but every piece of information should ground to one of them. So that's kind of one of the challenges that I think that we face, and we don't have a great answer for that yet. But I think the main takeaway is that the purpose of language is to inform a decision process. The other takeaway that I think is really interesting when we think about language, when we're talking about communicating with the decision process, is that language is very structured. And that structure actually matches really nicely to the structured decision processes, and it suggests that humans are using very structured decision processes. Okay, so for example, we have this class of words called verbs, and those are actions, right? Those are 100% names for actions. That's what a verb is, okay? And we have common nouns like tree or car, and those are names for objects. So that means that the decision process that you're in has objects, and not only that, it has object types, because a common noun is not the name for an individual object, it's the name for a whole type of, collection of objects, like all cars, right? So that says something about the state space that you're working in. Like, why are humans generating this particular type of structured language? Well, one hypothesis that I, am floating now, not knowing much about language, is that actually reflects the underlying structure of the decision process. So we have this workshop paper that came out last year. 2 students, Rafael and Roma, kind of took the structure of language that everyone agrees is there, like there's parts of speech, and they include verbs and nouns and all that sorts of stuff, and says, okay, like, let's look at classes of decision processes, like object-oriented decision process and these sorts of things, and let's see which of these parts of speech would occur in such a decision process, right? And so, for example, there's no reason to make a factual statement about the world, like the staplers in another office, if you're in an MDP. If in an MDP, you can always observe everything you need to observe about the world at every time step. There's no reason to have declarative factual statements. You have to be in a POMDP for a sentence like that to make sense. And you have to be in an object-oriented MDP in order to be able to talk about, to use common nouns, right? It only makes sense. And if you want to use adverbs, which describe the operation of an action, that modify the operation of action, you have to be in a decision-making process where the actions are parameterized, so you can change how they're executed. Right? So at the same time, we also kind of thought a little bit about how we might merge language and these kind of abstract symbolic representations, right? How are we going to ground to these things? So we had an RSS paper last year where what we did is we paired robot demonstrations and language. So we took a robot demonstration trajectory, we ran a skill discovery algorithm on it, which basically just segmented the trajectory into skills. And then we got 2 types of objects out. One is we applied our skills to symbols framework, and we got a symbolic representation that mostly described the termination condition of those skills. And we got verbs that looked like, okay, here's how to turn around a corner, right? And then we took the language, oh, why is it not clicking? Click, there we go. We took the language. So let's say you have sentence verb to noun, like walk to the corridor. And then the verbs kind of match to the segments, and the nouns kind of match to the termination conditions. And we were able to get a really nice thing where we learned the grounded symbolic representations and we mapped the language to that. So this is mostly the work of Nakul Gopalan, who was a PhD student here, is now a postdoc at Georgia Tech. Really, really smart guy. Okay, so just to sort of show you how that works, I think this is the sort of teleoperated robot data. So we generated these sample trajectories, and then we got language from humans labeling these sample trajectories where they just kind of labeled them, and then we learned a seek-to-seek model. Well, first we segmented them into skills. So we did that jointly over a bunch of trajectories, and then we learned to map those that language to those skills and symbols. So these are like this is a symbolic piece of information learned, which corresponds to being in an open corridor. And then you're able to give the robot a command, like go to the end of the corridor and take a right, and then it will run a little planner that executes that thing based on reaching those symbolic representations. Right, so we've got like a closed loop, right? And one of the things that I argue is that this is totally necessary for human robot communication. Right? You can't communicate at the level of pixels and motors. That's not going to fly. You have to communicate at these higher level abstractions, and then you can give it quite complex commands, and it's able to follow them really nicely. It's able to sort of execute these fairly long things autonomously because it can map those words to the learned symbolic representations. So that was at RSS last year. It's a really nice paper, and credit to Nakul and Eric, who are the students who did the work. Okay, so my sort of takeaways from that are, for integrated embodied general AI, which is the same thing as AI in my opinion. Everything else is not. The sort of mildly controversial statements maybe I want to make is that language is for informing sequential decision making. That's what it's for. Okay, so therefore you need to ground language into sequential decision making formalisms, not videos or images. And also that the structure of human language suggests that humans have highly structured decision process models, right? They have objects, they have classes of objects, it's a partially observable situation, obviously. They have parameterized skills that they can modify in response to adverbs. All these sorts of things are there. And that suggests that we should be building quite elaborate, actually, symbolic representations. I think that language is necessarily abstract. Language is discrete. And so we are talking about discrete abstractions necessarily. And so you have to ground to an abstract representation. And general AIs will have many such abstract representations, right? We have to give up on the idea that there'll ever be one that solves everything. In fact, instead, you should be learning them on a task-specific basis. And one open question is, which of these task-specific representations should you target once you've got some language? But I think the even deeper takeaway is that we have to deeply understand what the symbolic representation should be, under which circumstances are they discrete, under which circumstances are they continuous, how would you learn them, how do we make that stuff happen efficiently, and what do they mean, how are they grounded exactly, because without that, we're not going to be able to ground language into anything of use. And just to remember this big picture, like I think this is a really nice way of viewing and reintegrating AI, bringing all these kinds of things. There's a role for path planners, there's a role for alpha beta pruning, there's a role for policy search. All these things are actually useful in a general AI toolkit. The question is, how do we get from a general agent to the formalism in which they can be applied? Okay, that's it for my talk. Hopefully I have a couple minutes for questions and I didn't go too far over.
Thank you very much. We have time for one question, and there is one in the chat. Here,
Yes.
the question is, does the new language model, like BERT or GPT-2 or 3, can have a positive impact on your research? Would you be able to leverage on them to enhance the learning capabilities of your model?
Yes, you totally could. So I don't remember the details of how that model was learned, but yes, you could totally. We need to ground to symbolic representation. But one way to think about all those things is they're just really good priors in a kind of Bayesian system, right? So they're really good priors over sentences, and so in any Bayesian system, you should be able to use them to be able to inform stuff. But for me, that's the compelling question is like, where exactly do you ground to? It's almost not about the effectiveness of the algorithm, right? Like the algorithm is almost neither here nor there. It's like, what are you mapping to what? If that makes sense. If we don't map the right thing to the right thing, then it's all pointless. So super quickly, Tom asked, storing much representation poses a challenge. Yes, but for now, I'm not bothered. Even if it's like 50 terabytes, who cares? That's not the, first we make it happen, then afterwards we worry about we worry about compression and practicalities. First we get the right math down and the right principles in place.
Okay, great. Thank you very much again, Professor George.
Thank you.
Konidaris.
Great. Thank you all.